We're going to talk about circles and lengths of segments is our topic. Okay, so far we've dealt lots of stuff with, inscribed angles. Last time we had a point outside a circle and so forth, right? Today, we're going to have some relationship with circles and length of segments. So there are many sort of nice relationship you get with circles and length of segments. Take a look at the theorem here. Who wants to read this for us? How about, let's see. Eric, go ahead.
When two chords intersect inside a circle, the product of the segments of one chord was the product of the segments of the other.
Okay, so when two chords intersect inside a circle, we sort of had that before, didn't we? Right? Yesterday we had that. Okay, and we talked about intersected arc and so forth, right? This time it's a little bit different. When two chords intersect inside a circle, then the product of the segments of one chord equals the product of the segment of the other chords. Here's a picture. You see how we have the two segments now when the two chords intersect?
Yeah.
You got segment R, S, and TU. Turns out if you multiply R times S, it'll equal to T times U every time.
Oh.
Okay? Yeah, look. You see we have the two chords, right? You see where they intersect? And you separate this into four segments, right? If you multiply R times S, the segment of the first chord, that's always going to equal to the segment of the other chords, T times U, the length of these.
That means they're in proportions.
Very good. So Joseph said, because that means they're in proportion. What's going to be help us to prove this? Hold on. What do you think?
Yeah,
Similar triangles, right? Because you know that the similar triangles, SAS.
SAS.
R like A, AP, DD, and angle P.
No, I don't think it's going to be SAS.
Angle APD, angle CPB. Right?
No. Okay, so take a look at this.
Vertical angles are vertical.
Yeah, but that's not SAS is
Side angle side.
No, angle A equals angle C, angle D equals angle B.
side angle side what? Similarity theorem?
Similarity.
Well, you don't know they're in proportion, the size. That's what you're trying to prove.
Oh,
Okay, so be careful. It's not going to be side angle side similarity theorem.
not yet.
But no, not for this one. So take a look at this, and you're right. You need those two triangles to be similar. Once they are, you know that R over S is equal to what? T over U. If you have that, then you know that what? Or is it R over S or is it R over T? It'll be R over T equals to what? U over S. Then you could use the property of proportion, right? Then you get RS equals to TU, right?
Yeah.
Does that make sense? So then, if we could show that the two triangles are similar, we're done, don't we?
Yeah.
So I want you to think about as a group. Go ahead. How are we going to say that the two triangles are similar? Go ahead. I'll wait for you. Okay. So take a look at this. We got the same picture. As you can see through, right, through 2 points, there's exactly one line, right? So we do through these auxiliary lines. We get two triangles. All right. So a lot of you said this was pretty straightforward to see. You know that these two angles are congruent because these are. We need one more, because in order for us to show that the two triangles are similar, we need one other angle that are congruent. Okay, a lot of you see it. How about, good, I'm glad a lot of you see this. How about Eugene? What do you think?
Angle D and angle B share one arc.
Angle D and angle B, these inscribed angles share what? One arc, same arc right here.
Yeah.
So do the other one, you're right. Okay, so yes, very good. So, hold on. So we know that you see this inscribed angle ADC and ABC, right? So they all share, therefore this has to equal to that, those two are congruent. Some people say, wait a minute, the other one also works. Look at angle, the inscribed angle DAB also share the same arc as this inscribed angle DCB, right? So guess what? Those are also congruent. So you could use angle in any angle you like, okay? So you get angle by angle, two triangles are similar, correct? Which are the corresponding sides then? Well, R over, this R is the one that's opposite of this angle D, therefore what? R over T equals to what? You see how those are the corresponding vertices? And what about u over what? Because u is the one opposite of this angle A, therefore this one u over s. Okay? So therefore, using the what? Property of proportion. Okay, hold on. Okay, so who can tell me what we get here? From here? Jesse?
Property of proportion is, you get R times S equals T.
Yeah, and is that what we have here, Jesse? Okay. Any question? Does that make sense? Easy enough? So that's what this proof is. Okay, the rest of it. Okay, let's move on to then other ones. There are 3 theorems to talk about. Okay, so here we go. Second theorem. How about somebody read this for us? How about Noor?
When two secant segments are drawn through a circle from an external point, the product of one secant segment and its external segment equals the product of the other secant segment and its external segment.
So what does that mean? Here's the picture. So basically, you see how you have a point outside a circle? And you have 2 secant segments, right? So, yeah, but now secants align, but right now we're talking about secant segments. We said we could talk about them as a segment, remember? So we have 2 secant segments are drawn from the point outside a circle. The product of one secant segment and its external segment equals the product of the other secant segment and its external segment. So it's a little bit different. Look, it's R. This whole thing, R times S equals to what? T times U. It's not this one here. You see the segment AB? Unlike the other one, it's not AB times S or anything. Okay, be careful with this. We're talking about the product of the whole secant segment times the external segment, the S. You see that? Okay. And whenever you get something like this, a lot of you notice, what are you going to need? If you have R times S equals T times U, you're going to get 2 triangles that are similar. You know what I mean? Just like the one before. So which 2 triangles? So I want you to think of this. A lot of you see it, okay? First, write it down. And then if you're done writing down, figure out which 2 triangles we need to have them similar. And see if it works out. It's going to be very similar to the one that we just did before. All right, so take a look at this. Again, it's very similar to the one we just did. What sort of auxiliary lines do you think we're going to need here? How about Emily? Any guess?
Either AC and BD, or
Oh, no, you don't want to do it there.
AD and BC.
Yeah, because you want to talk about 2 triangles.
Yeah.
So I think the best way is be the one that like this. And
He's doing the one that I said.
oh, okay. Yeah, you said either one of those. This will the one that will work. So take a look at this. If I were to draw.
That's the one I said.
Oh, okay, good. So if you did this, you could see the 2 triangles. I see a triangle that goes like this, right? Which is a P, a D.
A, B,
APD, APD, right? Do you see APD right here? I'll do that in red. You see how?
Oh, yeah.
Yeah, okay. And then I'll do this in blue. Blue. You see this one? Okay, that's a hint. Go ahead, everybody, think about this. Oh wait, this is the other one. Okay. Okay, do you all see both of these triangles? I kind of separated them. Is that okay? If these 2 triangles are similar, that'd be nice because I'll be done, right? First of all, I see an angle that's congruent. Anybody see that? Okay, hold on. Okay, everybody should see this. Okay, how about Ryan? P. I would say the same thing. You see how they're sharing the same angle right here? Okay, both of them are okay. I need one more. Anybody see the other one? Okay, a lot of you. How about? I'm glad a lot of you see it. How about Nina?
Angle C and angle A because they share an arc.
Yeah, look, angle C. You see how this angle C? This is the arc that we're all looking at. You see that arc?
Yeah.
Look at this angle. This is an inscribed angle right here, right? ABD. Hello? And what else? What else? BCD. Correct? They both sharing the same. Therefore, this angle must be congruent to this. So by angle, the 2 triangles are similar. So what are the corresponding sides? R over what? T is equal to what?
S over U.
Is it S over U or U over? Okay, be careful. Does the order matter here? If you're gonna start with R, right, to T, the red to blue, you gotta go red to blue. Be careful. R over T equals to U over S. So when you multiply, when you do the by proper proportion, what do you get? R times S equals to T times U. Does that make sense? So it's really similar to what we had before, right? Here we had these two triangles similar. Now you have the triangle that's outside of the circle similar. Yes? Okay, so, and of course, that's what we have. Any question? All right, good. We got one more theorem to talk about then. Okay. Let's move on. I have the same picture again. Well, what do we find? Let's review a little bit. What did we just find? If you have a point outside a circle, you got two secant segments. What's true? What was the result that we got here? R times what? R times S equals to
T times U.
T times U. Are we okay?
Yeah.
Now, what if I move the other secant segment a little bit below than where the C is? Is that okay? Same thing. Okay. R times S equals to T times U. Would you not agree?
Yes.
Now, okay, somebody guessed it. What if the C, I move it all the way down so that C and D are at the same point? Any guess as to what you're going to get?
Oh, I know.
Okay, hold on. How about Alvin? What do you think? What do you think the result might be? Okay, so let me help you, Alvin. I know. I mean, it's just a guess. It's a guess, right? Alvin, watch this. In this picture, you know how we got R times S equal to T times U? This is always true. So will this be if I change the C a little bit down? Now, if I make C all the way down here where C and D meet, right? So basically this becomes a tangent. R times S equals to, guess what? T times U, which is
1.
well, T times U, they're both same thing. So either T squared or U squared. Is that okay? Turns out that's the case, right? So here's the theorem. Do you understand what we're saying here? So somebody read this for us. This is the summary. How about William? Go ahead. In the first two, a little bit louder.
In the third diagram, U and T both become equal to the length of the tangent segment in the equation because R times S equals to 1. This result stated below will be proved more formally in exercise 10. As in ordinary terms, the term tangent segment can refer to the length of the segment as well as to the segment itself.
Okay. So here's the theorem. Just like the result as up here. When a secant segment and a tangent segment, do you see how this was? We did this last time too. Remember one with the arc measure? Remember that? Now this time it's a bit different. When a secant segment and a tangent segment are drawn to a circle from an external point, the product of the secant segment and its external segment is equal to the square of the tangent segment. And notice, both of these theorems, they never talk about any segment that's inside the circle, do they? It's always the secant to the external segment. Please keep that in mind. Okay, that's going to be helpful for you when you actually are doing some homework. Don't get them mixed up because people, right, use the wrong segment to multiply. It's always the secant segment and the external segment, okay? So what this theorem is saying is this. If you have a secant segment, right, and a tangent, guess what? R times S is always equal to what? T times T, or whatever U and T are same, so U times U. Do you understand what he's saying? T for tangent. I like that. Okay. Does this make sense? So let's do some example. Hold on. Let's see if you really understood. Take a look at example 1. Okay. We talked about 3 theorems today. Guess which one this is going to be useful for? The first one. The other 2 had the point outside the circle, right? The first one was the only one where you had 2 chords intersect inside. Thank you. Go ahead and find by your backs. I'll wait for you. Everybody try. All right. I think most of you are done. Okay. How about, what did your group say? How about Lauren over here? 4. Okay, you're correct. Lauren, what was the equation that you used for this?
3x squared equals 28.
Yeah, because from the theorem previously, we know that x times 3x, right, equals to 6 times x, right? The product of these segments, they're always going to be equal, right? If they're chords, right? Intersecting the circle. Easy enough? Okay, then try example 2. Okay. Here we go.
Oh.
Now, let me give you a hint. Take a look at this example. You got a point outside a circle. Do you think it's going to involve the first theorem we studied or the last two?
The second and the last.
Okay, go ahead. Everybody try. Find x, y, x and y. Go ahead. Everybody try. Hey, this is a classic question where people mess up on the test a lot. They do this. 5 times 4 equals to x times 3. Okay. Why can we not do that? Because that'll be wrong. You don't want to do 5 times 4 times x times 3. Joseph, why not?
Because that's a wrong theorem.
Yeah, well, there's no theorem that tells you that to do that, right?
Oh yeah, I copied this guy.
So yeah, so what do we have to do? What's the correct way? What does the theorem tell us to do here? How about Akila?
Should I read it? Or should they just tell me?
Oh, tell me what to do.
Okay, so 5 plus 4 times 4.
Yeah, you need the whole segment, not the part of it. What's the whole secant segment here? Not secant. Yeah, secant segment. 9, right? Because 5 plus 9 times what? Is it the one inside or the outside? What do we multiply the 9 with? Outside. It's always the outside, okay? Remember the last two theorem. Don't multiply this with the 5. Okay, that's how you get it wrong too on the test. So it's going to be 9 times the one outside. 4 equals to what's this whole thing then? 3 plus what? X. 3 plus x times what? X or 3? 3. No one outside. Okay, be careful. So that's how you find x. There's your equation. That's the second theorem we talked about today, correct? You see where they get 4 times 9 equals to 3 times 3 plus x? And when you solve, of course, you should get x equals to 9. Is that okay? What about then for y? Again, it's a so now that we know what x is, you need to know that what x is, right? To figure out what y is, correct? So you could tell me what to do. Now we're going to do what? Johan?
So you do 12.
Good, 12 because this whole thing is 12, right? 12 times
3
equals to
y squared.
y squared. Okay, does that make sense? And you get y equals to 6, right? What about negative 6? Don't you get square root of plus or minus 36? Yeah, y can't be negative. It's just
Negative 6 length. What
right,
about
exactly. You can have
backward?
that. So therefore, the y equals to 6. Does that make sense?
Yeah.
Please be careful for using the last two theorem, guys. I'm telling you, you're gonna use the whole thing with the external segment, not the one inside. Please don't do that because so many times people do that and get the whole thing wrong. Okay? So, and you know the reason why. Okay? All right. Let me ask you one other thing here. Okay, here we go. Okay, I want you to all take a look at this right now. Guys, let me ask you something. If I have this angle to be x,
Ooh, Pac-Man.
yeah. Now, what can you tell me about? All right, this is important. What can you tell me about this arc right here that intercepts? Who could tell me? It's going to be 2x. Very good, very good. That's easy, right? Hold on. Shh. Hold on. Okay, so what if I did this? Okay, give me a sec. Let me draw something. Yeah, I have a ruler here. That's good, right? So take a look at this. What if I did this? What if I have this chord? What can you tell me about the angle that this chord, the blue one, and this tangent?
The angle is x. The angle
Okay,
is
what can you tell me about this angle right here?
x.
The chord and this tangent, because how do you know this is x again?
Theorem.
This is half of the intersected arc. You guys remember that's one of the theorems,
Yes,
right?
they both use the same
Okay,
arc.
would you not agree? Okay, so let me just do one last thing. Then I'm going to connect these. They're gonna meet us somewhere right here, right?
Little triangle.
Okay. So let me ask you, if I had this, okay, knowing this now, okay, are we good with this? We got a whole big triangle over here, okay? Do you see any two triangles that are similar? I want you to think of as a group. Go ahead. I'm gonna call this A, B, CD. Go ahead, everybody think about, do you guys see any two triangles that are similar? I'll wait, hold on. Alright, who can tell me the two similar triangles in this case? How about, give me one of them. How about, Charlie, what did your group come up with? Triangle? Triangle ABC, yeah. So what is that similar to? The other one then? Huh? So triangle ABC, the big one, ABC is similar to which one? Yeah, because look at angle A has a measurement of x, right, Charlie?
Yeah.
So which other triangle has a measurement of x?
C.
C. So C, triangle C, right? And look, aren't they both sharing the same angle here? So if it's ABC, it's going to be CB what? CBD. Would you not agree? CBD.
CCE.
Alright. Would you agree? Do you see how the two triangles are similar? The big one and the one inside here? Right? Because we knew that if this angle is x, and then, this is how we construct it. Now let me ask you this. Class, if this is true, what do you know about two similar triangles? This is similar by angle, right? What do you know about two similar triangles? The corresponding sides are in proportion. So let me ask this. How about, you see this length AD? AD over what equals to CB over what? Oh wait, AD over what? Okay, so sorry, my bad. AD is this big triangle right up here, right? AB. Let's write down some of these then. Corresponding over AB over what? CB, right? CB is S2. How about I want to compare CB over what?
Geometric mean?
No.
Oh, never mind.
AB over
DB.
AB over CD equals CB over what? Look, CB in this big right triangle is opposite of the angle x, right? Which side is opposite of angle x in this smaller triangle? What? BD, right?
Wouldn't it be DB because
Yeah, DB and the CB. Oh, is it DB? Okay, DB. Are you okay with that? Does that make sense? Look, if you don't see it, go ahead and ask your group. Why is this true? Go ahead. I want you to think about this. Why? Okay, I think a lot of you see it now. It's easiest to see. Look, guys. AB, this whole thing in this big triangle, it's opposite of the angle. This whole angle right here, right? So that thing. What about for the smaller one? Well, it's the opposite of this angle D, right? So it's got to be CB, which is equal to what? Where's CB opposite of within this big triangle? Opposite of the angle X, right? Well, in this triangle, smaller one, which side is opposite of the angle X? DB, right? If that's true, let's use the proper proportion and we could say what? AB times what? DB is equal to what? CB squared. Does that sound familiar?
Well, the theorem.
It's the last theorem we talked about today, correct?
Yeah.
So on your homework tonight, you're going to have to prove it. This is how you do this. Okay, does that make sense?
Yeah.
Any question? And it is this geometry mean. You're right. Very good. Some of you see it. This is a geometry mean. Very good.